Alright, so our next review topic is how to find areas bounded by curves. Um, so really the main problem here is figuring out what it is that you're actually looking at. We need to know how to graph things, of course. Let's see here, so let's get started with this one. And let's see here. So there's my y-axis and x-axis. Let's see here, y equals x plus 6. Well, that's a line with slope 1 with, y-intercept of 6. So it's, I don't know, roughly speaking that, right? And then y equals x squared. Well, that's, crudely speaking, that thing, right? Now this is a pretty nice shape. We're trying to find the area of that. Here, let me find something real quick. I guess this will work. So we're trying to find this area in here. And so what I always do with these problems is I try to draw a typical approximating region. So basically this has a well-defined top and bottom, right? So I can draw one of these little rectangles at each point with a well-defined top and bottom given by, well, let's see here, the top y is this, right? And the bottom y is x squared, right? And so dA, the little bit of area subtended by one of these guys, right? The thickness, of course, is dx, right? And so like dA, the little bit of area right there, is the top y minus the bottom y times dx. Now, in terms of the specifics of this problem, what that gives us is dA is equal to x plus 6, right? X plus 6 minus x squared dx. And that's true for blank less than or equal to x less than or equal to blank. Now, I haven't figured out what goes in the blank yet because I don't yet know what these points of intersection are, right? So we're going to have to figure out what are these points of intersection here and here. Points of intersection. Well, how do you find them? Points of intersection are places where both, which are on both graphs. So that means that y equals both x plus 6 and x squared. In other words, you're looking for where the y at the top is equal to y at the bottom, which is x plus 6 equal to x squared. Of course, this gives me x squared minus x minus 6 equals to 0. I guess completing the square isn't probably the best path here. Instead, I'm going to do x minus 3 times x plus 2 equal to 0. And you're like, see, completing the square is not always best. Fine, you got me. Sometimes we can factor. All right, x equals to 3. So there you go, fill in the blanks. Minus 2 less than or equal to x less than or equal to 3. For every such x between minus 2 and 3, we can draw a little approximating region, infinitesimal vertical rectangle, and then philosophically, something I haven't shared with you yet, but I should have, perhaps, is that, of course, the definite integral is nothing more than the continuous sum, right? So I add up all these little dA's, and the way we do that, of course, is just integrate minus 2 to 3, right, of x plus 6 minus x squared dx. All right, and then from here it's just integration. Here it's just mindless algebra. 1/2 x squared plus 6x minus 1/3 x cubed. I have to take that, evaluate from minus 2 to 3. So that's 1/2 of 9 plus 18 minus 1/3 of 27. Don't really need these parentheses, but I'm putting them there anyway. Minus 4 over 2 minus 12 minus a minus, which is plus 8 over 3. All right, so that is, what is that? This is 9, so that's 9. 9 over 2 plus 18 minus 9 is plus 9. Let's see here, that's 2. 2 minus 12 is minus 10, so plus 10 minus 8/3. So, oh, I don't know. Apparently this works out to, let's see if I'm using a book example. Oh, exciting. Alright, so I'll change this to, tell you what, I'll change everything to sixths. Looks like we've got a half and a third, so everything should change to sixths, right? So this in terms of sixths is 27. This is 54. That's 60. And let's see here, in terms of sixths, multiply by 2/2 minus 16, right? And sorry if I'm going off screen. Let's see here. So what we got is, should really probably get out a calculator. Oh well. Let's see, we got 70, 81, 141 less 16 is 125. 125 over 6, which is also the answer that is in Anton's 4th edition. This, for what it's worth, is example 2 on page 396 of Howard Anton's 4th edition of calculus. Okay, so there it is. There's a good example. Let's do another. Find the area bounded by x equals y squared and y equals x minus 2. So my usual procedure here is to try to sketch, at least make an attempt here. Now, this is a sideways opening parabola, right? That's what that is. And y equals x minus 2, well, that's a line with slope 1 with y-intercept minus 2. So it's basically just this guy, give or take. All right. So the area bounded is pretty clear. It's right up in here. So I want to find that area. I'll find the points of intersection to start with here. What are these points? Those are places where we have both equations are true, right? So I can solve both of these for x. Like we have x equals to y squared, and also this goes to x is equal to y plus 2. So I would just point out that this is the left x, whereas this is the right x on the region. Anyway, so we need to solve this quadratic equation y squared minus y minus 2 equal to 0, otherwise known as y minus 2 times y plus 1 equal to 0. So we have intersection points of y equals to minus 1 and 2. All right. Then, again, I draw my little approximating region. This time, I don't want to take vertical rectangles because that's awkward. See, if I did it here versus here, here the top and the bottom is both given by the x equals y squared curve, whereas over here the top is given by the x equals y squared curve and the bottom is given by the line. That means I'd have to break up the integral into 2 pieces, and if I can avoid that, I want to. So instead of looking at vertical approximating rectangles, I look at horizontal approximating rectangles. Although I guess I really should say they're not approximating, they're infinitesimal rectangles. So here dA for this, the thickness of such a rectangle is dy. Little change in y, right? And so like dA is going to be the right x minus the left x. That's the width of this approximating infinitesimal rectangle, and the height is dy. And there you go. And of course, to be more specific, we have dA equal to, let's see, the right x was, what was it, at y plus 2, and left x was y squared, so minus y squared dy, and that's good for minus 1 less than or equal to y less than or equal to 2. And then to find the net area, I integrate dA, take the continuous sum of the infinitesimal areas, which in this case amounts to doing this definite integral from minus 1 to 2 of y plus 2 minus y squared dy, which is 1/2 y squared plus 2y minus 1/3 y cubed. You take that thing, evaluate from -1 to 2. The arithmetic isn't especially exciting. Let's see here. Oh, Anton actually has done it by the other way. Funny. I don't know why he does that. I mean, you can do it, but yeah, whatever. Maybe he's about to redo it in the next page. Oh yeah, that's his point. He does it the vertical way and then the horizontal way, just to contrast. So y squared over 2 plus 2y minus y cubed over 3. So this works out to 9/2. I'll spare you the arithmetic. All right. I mean, I'll spare myself the arithmetic. Anyway. Example 3. Find the area bounded by y equals 1/2, x equals to 0, x equals to pi, and y equals sine x. Now, to be more specific, this is the picture, and I think it makes sense what region I'm talking about. The area bounded between 1/2 sine x, 0, and pi. It's got 3 parts to it. It's got this piece. It's got this piece in here. All right, and it's got this piece over here. All right. So this time, there's a big difference, say, between like over here or over here, right? So in those cases, let me say dA1 and dA3. dA1 and dA3, same setup, right? It's going to be the top y minus the bottom y, which in this case, the top y is what? It's the blue line, right? So that's 1/2. And the bottom y is sine x. Sine x is below 1/2 in these two regions, right? And the thickness of the infinitesimal rectangle is just dx, right? And that's true for 0 less than or equal to x less than or equal to, what's this intersection point? In other words, where is sine of x equal to 1/2? Well, I talked about that a video or two ago. It was pi over 6, all right? Well, that's the first place it's a half. It's also a half over here, right? That is 5 pi over 6, right? It's a little bit shy of pi. All right. So for these two regions, we have those approximating, well, not approximating, those are the infinitesimal areas corresponding to dx in those regions. Now, in the middle, let's see here, I'll use orange. In the middle, on the other hand, sine is the winner, right? So in here, we still have dx, right? But it's pretty clear that dA2 is equal to, excuse me, sine x minus 1/2 dx, and that's going to be true for pi over 6 less than or equal to x less than or equal to 5 pi over 6. So if I want to find the total area here bounded by these curves, I have to add the area for region 1 plus region 2, right, plus region 3. Now by symmetry of the problem, it's pretty clear that area 1 and area 3 rather, are equal. So let's just cut our work by 1/3. So the area is going to be 2 times, and I'll take the easy one to calculate, integral from 0 to pi over 6, right, of dA1, which is 1/2, minus sine x dx, all right, and then plus the integral from pi over 6 to pi, 5 pi over 6 rather, of sine x minus 1/2, right, dx. Now, now, of course, once you write this down, if you have more sense than I do, you might not even written this. I'm just showing you how to think through it in terms of the approximating rectangles. There is, of course, a cheat move here that's even easier, right? And you can rediscover that by just rearranging these integrals. Let's see here how to do this. Curses. Well, I guess. All right, so I see something now. I'm going to undo that and say plus the integral to 5 pi over 6 to pi, right, of 1/2 minus sine of x dx, right? Let's see here. Oh, fine, I'll stick with it. I'm sorry, guys. Ignore me 2 times. There's some tricky way to do this in terms of subtracting areas, but I'm not. Let me just stick with my original approach. Fine. So this is 2. 1/2 integrates to x, but that's just going to be 2 times pi over 6, right, from that 1/2. And then plus 2 cosine x, because this minus sine x integrates to cosine x, evaluated from 0 to pi over 6. And then, let's see here, then plus, I'll use in parentheses, minus cosine x minus x over 2, evaluated from pi over 6 to 5 pi over 6. All right, so I got myself pi over 12 plus 2 cosine of pi over 6 minus 2, cosine of 0 is 1, right? And then over here I've got plus, let me stick with the program here, minus cosine of 5 pi over 6. I'm going to go ahead and do both the cosine terms first, sorry if that bothers you. Cosine pi over 6, because minus a minus gives me a plus. And then I'll take care of the x over 2 terms, and then minus 1/2 times 5 pi over 6 minus pi over 6. All right. Sorry, I get a little bit messy in here. All right. Well, let's see here. Can anything cancel out? I don't know. Oh, I've got 3 of these guys, huh? And these are also, this simplifies to what? That's 4 pi over 6, so that's 4 pi over 12, right? And so we get a total of 5 pi over 12. It's my constant term from those. Oh, and then there's this minus 2. And then let's see here, plus 3 cosine pi over 6. Let's see here. I got this one, this one, this one, this one, and all that ones. I'm just missing my minus cosine of 5 pi over 6. All right, now the cosine of pi over 6 is what? It is the square root of 3 over 2. I don't remember the cosine of 5 pi over 6 right offhand. Let me just work it out real quick. Cosine of 5 pi over 6, well, sorry, like what is the cosine of theta plus pi? So that would be what? Cosine theta, cosine pi, minus sine theta sine pi, right? And so sine of pi is 0, cosine of pi is minus 1, so cosine of, that's just minus cosine theta, right? So what that tells me is that cosine of, how do I say this? So cosine of pi over 6 is what? It's like, sorry, this must be painful to watch. Goodness gracious. Sorry. So if I put theta equal to minus pi over 6, so like pi minus pi over 6, that's cosine of 5 pi over 6, right? Sorry, there are other ways to calculate this faster. I don't have a calculator right on hand, so I'm just working at it. So that's minus cosine of pi over 6, which is minus root 3 over 2. So in fact, this is minus the square root of 3 over 2, and that is, of course, just the square root of 3 over 2. So minus minus gives you, so I get 5 pi over 12 minus 2, and I've got, it turns out 4, the square root of 3 over 2, otherwise known as, fine, enough, I'm tired of this. Are you tired of this? I'm tired of it. 5 pi over 12 minus 2 plus 2 root 3. Now, Did I make a mistake somewhere? Is this really the real answer? I don't know. I tried to do it carefully. But anyway, the setup is probably most important here. I hope you see the importance of identifying which is the top curve versus which is the bottom curve, because if you don't do that, you'll get the wrong answer. One more example here. Find the area bounded by y equals 1 over x squared, y equals x, y equals 4. So let's see here. Y equals 1 over x squared is what I like to call the volcano curve. So it's like this guy. Right, it's got a vertical asymptote at 0. It does not curve back up over here. Sorry. And y equals x, well, that's this guy. Right? And then y equals 4 is, let's see here, I'll use a different color. Maybe it's up here, I don't know. Right. So, you know, when you draw curves like this, sometimes appearances can be deceiving, but probably I'm on the right path here, that this is the area we're after, right? Let's see. So it looks to me like horizontal approximating, horizontal infinitesimal rectangles are the way to go here, way to model this area, because if I do that, I can again take this, you know, one approximating scheme for the whole thing, right? If I was to use vertical ones, it would be annoying because I'd have to break up into two cases because there's a different bottom here and here. All right. So my dA is going to be my right x minus my left x times the dy. The right, now I guess we need to figure out what is, so this is the right x, right? That's easy, but this one I need to do a little bit of work. So this says x squared is 1 over y, right? And so x is equal to the square root of 1 over y, plus or minus generically speaking, but we're where x is positive, so we choose the positive solution, all right? And of course that's 1 over square root of y. All right, so what we have is then we have dA is y minus, that's the left x, of course, 1 over the square root of y dy. And I suppose we need to figure out for what, you know, when is that the case. So for that I need to figure out the points of intersection. Well, the top is fairly clear. I mean, blank less than or equal to y less than or equal to, I know what goes up here, 4, all right? What's this point though? That point is where, I mean, you can find it however you want. I'm going to just plug these equal. So we've got y. We need 1 over x squared equal to x. That's where that's going to be true, right? That's where the y's match. So 1 is equal to x cubed. So x is equal to the cube root of 1, also known as 1. Now, x being 1, what's y equal to? Well, this is kind of an embarrassment of riches. We have y equals x, so therefore the y is equal to 1 there. So it's 1. All right, so now we're in business. Let's calculate the area. The area is going to be the integral from 1 to 4 of y minus 1 over the square root of y dy, which is 1/2 y squared minus 2 times the square root of y. If you doubt me on the second term, differentiate this. What do you get? 1 over twice the square root of y. But then times minus 2 cancels and gives you minus 1 over root y, which is what we have back here, thus showing that is in fact the right antiderivative. All right, and then evaluate. So that's 1/2 of 16 minus 2 times the square root of 4 minus 1/2 times 1 squared. I'll just put some parentheses here. Minus 2 times the square root of 1. All right, so that is 8 minus 2 times 2, 4 minus, that looks like 1/2. And that does look like 2. Minus minus gives me plus 2. So let's see here, I get 10, 6, 6 minus 1/2. So we can either write that as 5.5, although I don't do that too much, or, as I probably prefer, 11/2 at the moment. There is a time and place for decimals. Certainly in physics, decimals are preferred. Well, they may be demanded in physics. At least I do in physics. But anyway, hopefully a moot point. All right, so those are 4 pretty usual examples of how to find areas bounded by curves. And next, I'm going to showcase the other infinitesimal method. I mean, infinitesimal methods, generically speaking, the idea is take whatever problem you're looking at and chop it into like infinitesimal subcases, and then you add those infinitesimal sub things up using the idea that the integral is the continuous sum. And by this methodology, we can calculate areas bounded by curves, volumes, either by disks or washers, and then a variety of other physical things, like we can calculate the force on a dam, or the net work done by a variable force. Here, I'll just, well, let me start the next video on that. I'll stop this for now here.